to understand very clearly, okay, that what actually we are doing, because on the base of that you have many problems to solve, and also actually you need to do some kind of animation of the object is based on this scaling, based on this transformation function. And as we have seen, we are focusing this three of this transformation function: translation, scaling, and rotation. And we have seen that translation is actually the displacement of any object in the space. That means moving from one location to another location. That is actually the translation. The main actually feature of translation is some unit or up to some factor that object actually move from one place to another place, and object shape, size, that does not change in actually general translation when it happens. So that whenever I have an object is in actually it's a older position, you can say is a P. It's actually consists of many number of points. We are just considering one point for the definition, and we apply some translation factor that can be changed, because whenever in the space it has a change of that point is related with the two values of the x and y coordinate. So whenever it has been changing for the translation factor up to that tx or dx in the x coordinate distance, and the y coordinate distance, so that is dy or ty. So if we apply that, then the new position of that object we will get, and that is actually select p prime. So if p prime has the x coordinate is x prime and y coordinate is a y prime, so that x prime and y prime is actually that x plus that dx or dx, and y is actually the y prime is y plus that dx. That's actually we have seen. We have seen with an example as well that what actually it happens for that point, and with the column vector that we try to see, that x and y plus the dx and dy, that actually give us the new value for that x prime and y prime for the new points location. This is actually the translation. Then we found about the rotation. Rotation, we have seen that this is actually kind of a change of the orientation of that object. Again, the size and shape is not changed, rather than the look of the object is actually changing. It's changing. It's actually rotated the degree. So points are actually the old point, or maybe the object itself. It also changes the position when it actually rotates. And for rotation, the basic thing that we need actually point that on the base of a point that actually the rotation happens, and some degree of the rotation happens that we actually denote as theta. Okay, so we found actually the formula is this one is dot product for that column vector, that rotation function and the old point, that if we actually have a dot product, then we will get the new point. So what is actually the rotation function? Rotation function is actually that matrix cos theta minus sine theta and cos theta, and that can be actually applied with the old point, and we can get then the x prime and y prime. And we have seen that if we just do the dot product of these two matrices, then we get actually that x prime as we get x cos theta minus y sine theta, and y prime as we get actually x sine theta plus y cos theta. That is actually the formula we get. So if we can apply the theta value with the cos theta that value, or sine theta that value, and the value of x and y, then actually we can get the new points, actually the position. We have also a problem. We can also actually simple problem to solve that to understand. This is actually just a diagram is showing that on the basis of a point, that how actually this rotation actually happens. Say like this, home actually this shape has been theta degree orientation it has, and the new position it has. So whatever the point P we are actually considering for this object, the new point you are getting actually on that the space, so the new location actually you have after that rotation function applied. We said if it is going like a counterclockwise, like this way, as you can see in the diagram in here, that is actually a positive rotation if it is happening in the counterclockwise. And if the rotation happens this way, the clockwise, then it is a negative rotation. This is the convention for the rotation here. And we have seen that those two of the formulas we have said about x prime is equal to x cos theta and y sin theta. We have seen that how it can be generated. Okay, that x prime is x cos theta minus y sin theta, or y prime is actually x sin theta plus y cos theta. We have actually taken 2 points. 2 points. It's actually 1 point having theta degree rotation on the origin point, and the new position it got actually p prime. Now, from this movement, we have seen that whenever a point has been actually rotate on some specific degree on based of that origin point, then their actually positions are actually circular point. So that if we have a draw a circle on basis of that point and the distance of it actually radius, then we will find that that point is actually on the circumference it will get. So it will have a movement on the as a circle. So that's why we have actually considered that p to distance of that origin and p prime or the distance of that origin should be same as like in the radius if it is in the circular movement it has. So considering that actually condition, we taken that triangles, just added that line with the x coordinate. So we apply the trigonometric formula with that what is cos theta, what is sin theta, like that base by abscissa or maybe perpendicular line by that abscissa, so that we get that equation. Then we actually simplify more with cos a plus b or sin a plus b, those two formula for that equation, and then finally we reached in here after replacement. So this is actually the rotation function by how that we can get it. And then we are discussing about scaling. And we have seen that this function is actually related with the size, that changing the size of that object. And this is also relevant. As the shape is changing, if you change the size, sometimes it can happen that shape is not changing, but the size is getting small or big. Like in the diagram, you can see the left hand side, that object, the home shape is actually in a size getting small, but the shape is not changed here. So it can happen. This is also part of the scaling, the general scaling, this one. But it is actually a powerful function because if it is actually changing some of the dimension with x and y coordinate are two dimension here, any of the dimension have different way of changing, like one is 5 unit change, one is 4 unit change, then definitely started to change the shape of that object as well, not only the size. So this is the scaling. And also this increasing or decreasing the dimension can be done on the basis of that actually a point, that on the basis of that point we can count, like okay, this x coordinate x basis of that scaling factor, we are going to make it double. Okay, now if we want to count, you have to count from the origin, and then actually you can make it double. So that's actually the scaling is having also the scaling factor, and also same like the rotation, that is the old point with the scaling factor. If you have a dot product, then actually you will get the new points location. Okay, so as you can have like p is old point, which is actually x and y, and then we have that scaling factor, that s of x and s of y. As you can see in this x coordinate for s of x, y coordinate in here 0 on that case, and when it is y actually factor, then it is actually changing in the y coordinate base. So this matrix, if we have multiplication with x and y with this column vector, then we get simply like x prime should be s of x and x if we multiply, and y prime will be s of y and y. Okay, so that you can see here that x prime is s of x and y prime is s of y and y. And again, they need actually a point to count. Like you see that this from that origin point, it's been showing that the old position for p or that object is actually having movement of p prime. Now this is significant. Every time you can see that example, if we can give with an object, it's understandable for the changes, for the transformation. Otherwise it's very difficult. Like if I just consider one point in here, and if I apply that scaling factor on basis of s of x and s of y, then my new point position goes in here. Now what I will understand if I don't have that object? So the other 3 points in the corner that they have also applied that factor and they get a new position. Then you add those all point and you find the object. And then you can understand, okay, yes, this is now 4 times larger than the previous object that we had. So it is actually enhanced or it get extended of that size. Now that's why sometimes for the example we are assuming an object and we consider one of the point from that object, and then actually we are showing through it, so it is easier to understand. Okay. Because translation you can also see, okay, this point is moving from this point. Rotation also actually you can see, like it will maybe have some degree it has been rotated, so you just join it and you can find the degree. But the scaling factor you cannot feel unless you have an object to draw, right? Do you understand that one? Because we need actually that example when we'll go for a translation to understand. Okay. We also have discussed that translation like this one, as you can see that their scaling factors are actually same in both. Same means actually equal. Like s of x is 2, s of y is 2. So that what is happening? The x coordinate, that object is actually expanding up to 2 unit factor, and y coordinate is up like that extending up to 2 unit of factor, so that the object does not change the actually shape. It retained the same shape, but it's been extending, or either it's going large or maybe small. And this is actually called the homogeneous transformation. And if your scaling factors are same, and if it is not, then differential transformation, differential scaling, that is called. Now at this moment the values of that scaling factor that actually we are doing, if they are actually uh, if they are actually equal to 1 or less than 1 especially, then the object that's its size goes actually small. If it is less than 1, okay. And if it is actually if it is less than 1, then the size goes actually smaller, then it is called the reduction. As you can see, the it's getting the smaller size. And if it is getting large, that means greater than 1, then automatically the size is actually getting large. That is called the magnification. So either maybe you are doing enlarging the object, or maybe you are reducing the object. We have seen that if it is actually the value is 1, then it is actually no changes happens for that object. It's in the same position it will be. Mirror reflection, another function that we have seen. It's just we can take an idea that what actually it is. In object, a point or object we consider is having x and y coordinate. You can see in the diagram the x and y coordinate, that axis. So x and y axis actually divide the space on some, like y coordinate is actually the vertical way that actually it make a separation, like this is sorry in this vertical line make actually horizontal separation of the space, like one is actually up and down, right? Sorry, this one is actually make that left and right, these two side. So we can consider that like it mirror actually the position. So for p, for the y coordinate perspective, the reflection is actually this point, which is actually minus x and y. Okay. So the mirror reflection of y coordinate for that object is actually the minus, the x coordinate value will be minus. Then actually that object is actually the reflection that you get. Simultaneously, in the same way, for x coordinate is actually dividing that space in that vertical position, that up and down. that x and coordinate. So each mirror reflection is actually getting that x minus y, so that whatever you get actually the y coordinate value for your object, you just make it negative, so that this will come in this quadrant. Okay, so that's actually called the mirror reflection. A object can have, regarding this two of the axes, can have two position in the mirror. Okay, if you just consider that this is actually for that y coordinate basis for that one, and this is actually the x coordinate basis that one. Okay, so we have no function to apply in this case, as we are actually working on these three basic function, which is that translation, scaling, and rotation. So for scaling, we need to discuss something more. Then we are coming back again for rotation for one of the simple example here. Okay, in scaling, we said about the sizes as, and it's indicating that actually your new position x coordinate value and y coordinate value can be just simply having multiplication of that point, and with that x factor and y factor, that actually the scaling that we have. So finally, that we can gauge actually like this, as you can see here, that p is just denoting for one of the point, and we are considering an object to understand actually the changes of the size for that object. It's through the assumption that also you can take it. Here also it has been taken, like you can see for P is having some value, say like 1 2 1 2 3 2 3, maybe say like this point value. So if we have x coordinate value is 2, y coordinate value is 3, and we have a multiplication factor, say like 2 and 2, then 2 into 2 is 4, so new coordinate maybe you will get 4 for that point for 4, and the y coordinate you will get maybe 3 into 2 is 6, maybe the 6. So 2 and so 4 and 6 would be actually new points position. The same way, if we can take the same actually this point and apply that factor, then actually we'll get actually some new position of those points, and if we just join, then actually we'll get actually the new object then. That is actually about the scaling activity. Now we already said 0 and 1, that means your factors are in between 1 actually or less than 1, then definitely we get the reduction, the object get actually the smaller, say like these cases. So what actually happens, if you get a smaller object, then you are coming more close to the origin, right? So that's why it says the points are actually getting more close to the origin when the reduction happens, so that the scaling factors are in between 0 and 1. When you have actually more than 1, okay, then actually what happened, you are actually going away of the origin, that we will see as well. Now with this example of the reduction, you see that the scaling factors are 0.5 for x and 0.5 for y. So what is actually the new point location will be, so it is 2 and 5 is actually old, so 2 and 5 for that this point. Then if we apply that 0.5 and 0.5, what is the value we get for new point? If x prime is actually for p, then what should be the x prime? S of x into x, right? So 2 into 0.5 is actually what? 2 into 0.5?
1.
1, right? So that x coordinate value we get for that 1, and the y coordinate, the value 5 into 0.5, right? That means 2.5.
Yes,
So we
sir.
get actually the coordinate value for that p prime, that means this point we get 1 and 2.5. So 2.5 is actually, we may consider 3 maybe, so 1 1 2 3. So this is actually a point we get. So this point and this point, that having a movement for this one. Now same thing, that if we apply the same scaling factors, like it was actually maybe 1 2, maybe 2, it has the 2 into 0.5 is 1, and This is for the y coordinate. We have 1, uh, 2 as well, and also actually that will be 1. So 1 1 for this one. This one also, if we apply say like 1 2 3 4 5 and 1 2, so 5 and 2, maybe 5 will be 2.5, and that will be 1 2.5 and 1 will be actually new position. So this is 3 and then 1. So this point, now whenever they have been added, then the object actually you get, which is half size. That zero point 0.5 is actually scaling factor, as you can see in the both one. So that actually you get a smaller half actually size of that object. Okay. The same way that when we have larger than 1, the value for scaling factor, then actually it's going away from the origin. So it's going maybe that in away size, like when we have a value, say like s of x is 2 and s of y is 2 for the same point, then you can see it's automatically say it's getting double, right? The size of that is getting double. So 2 and then 5. So the x coordinate value will be 2 into 2 is 4 and 5 into 2 is 10. So 4 and 10, you can find the point is new point is now in 4 and 10 that position. The same way this one, if it is say like 1 and 2, this one is actually 4 and 2. Those, if you multiply that value, you will get those actually the points, and you add those that object, then actually you can feel how the object has been actually changes, means the shape of the object is also actually, sorry, size of the object is actually changed. Now, this is actually the basic scaling function. As you can see how they are related. Every time this scaling as well, you need a point to count. Okay, from a point to count, or on the basis of the point, and that is actually origin that actually we are doing, because whenever the scaling factor we are actually considering, and that factor we are actually applying on the point, then we are trying to find out actually the points, the coordinate from the origin. Every time we are actually counting that the origin, because that unit for zero point 0.5, unit for 2, they are also actually calculated from the origin, from that coordinate values. Now, if the scaling factors are actually equal, as in the previous example that you have seen, both of the cases that scaling factors are equal, s of x and s of y. Either maybe you are doing reduction, either maybe you are doing the magnification. Okay, but they are actually the uniform scaling, or in the homogeneous values that actually we get, right? Now, if we have that scaling factors are different, then actually different means s of x is 2, s of y is 5, then actually is the differential scaling. And this is actually a very powerful one. As you can see, it change in the size and shape as well. Okay, when you have a differential scaling, but when you have that uniform scaling or homogeneous scaling, then only change in the size. We have seen as well that only the size has been changed, but their shape does not change. They are actually having the same type of triangle that actually you can see. But whenever we have actually different values, then it changes. Say like what difference? Say like 1 point, which is 1 and 2 that we have, and then actually applied that s of x is 2 and s of y is 2. Then where actually it goes, that px is actually 1, so 1 into 2 is 2, the x coordinate is 2, and 2 into 5 is 10, so 2 10 is my new position. So 1 2 2 and 10, somewhere in here is a new position, that p prime that we get. If I apply the same other points actually with the same value, you can see that they are actually going in new position. Now, it was actually a square at the beginning, but look at the object now that actually we get is actually not square anymore. It is actually a rectangle, which is having the differences with their edges, and it only actually happens, as you can see, for that differential scaling value. Okay, as those unit of the factors are actually changed. Okay, so this is the differential scaling and the uniform scaling, how they are different. So these are actually, as you know, that important understanding for your Viva exam mostly. Okay, now For the scaling that we have seen, we just try to understand some of their feature. We also have checked with actually rotation that on the basis of that how we can get it that rotation factor, and with the multiplication of or the dot product of the existing point, then we will get actually the new points value. So we'll try to solve this one in a very simple problem that find the transform point p prime caused by rotating of P, which is 5 1, and about the origin through an angle of 90 degree. Okay, so what actually the element you need for the rotation? You have a point on the space which is 5 and 1, okay, on the space, and which is actually said about the origin that you are actually doing that rotation. So my point has been given. You must need a actually point on the basis of that you need to do the rotation. So that's actually it says actually that origin point it is on base of it. Now you have a rotation of 90 degree of angle. Okay, so how much degree you are having orientation, so that you can find out the new position of that point. Okay, so that's easy to find out, because as you have an equation, simple equation already you have for that rotation function. You already have theta is actually 90 degree, as you know that it has been doing it, and then the old points actually the value which is actually the 5 and 1. So the formula, if we apply that rotation function and the old point, so cos theta minus sin theta and sin theta cos theta, if we do that actually dot product, we get x cos theta minus y sin theta, and x cos sin theta plus y cos theta. Okay, this is actually the thing we get. Now if we put the value is actually that 5x is actually 5 and y is actually 1 and theta is actually 90 degrees. So 5 cos 90 minus 1 sin 90, 5 sin 90 plus 1 cos 90. Then you just put that value is 5 into 0, cos 90 is actually 0, sin 90 is 1, then 5 dot 0 and minus 1 into 1, and here 5 dot 1 plus 1 into 0. So we get here minus 1 and we get here for 5, because the others are actually 0. So minus 1 and 5 is the new position of that object after having that 90 degree angle. So if we just try to locate for that one in the graph, let me check for a, if we can quickly draw. That was actually that point was we had a point P was actually 5 and 1, right? And theta is actually the angle, or maybe we just write it here, angle is actually 90 degree, and about the origin, that is always you need to check on basis of which point you are actually having that movement. Okay, now if we have that one, we already apply that formula for and you have seen the equation already, and finally we get the point is actually that desired point that we have actually get the p prime is minus 1 and 5, right? That we have got, or minus 5 or 1? Minus 1 and 5 that we actually we got. So minus 1 and 5. So somehow if we just have, can we, if we just have a coordinate, we have needed a coordinate. just take few of the lines that we needed. Then okay, I think that would be sufficient. So like this is actually maybe our that point. So our actual P was in 5 and 1. So this is maybe 1, 2, 3, 4, 5, and then the 1. So say like my point was in here, P, okay, and that is actually having that value P, 5 and 1.
Acha.
And then we had that new point is -1 and 5. So this is -1 and 1, 2, 3, 4, and 5. Say like this is actually the point we get, and this is maybe that pixel, or maybe you can take actually the coordinate as here as well. That is also actually fine, and that would be better, because if we, whenever we want to draw to check like whether it is 90° or not, if you just actually from the origin, if you just draw the line, okay, I think maybe if we just draw the line from the origin to that point, here now you can check, then you will find that this is actually the 90° that rotation has been done. Now this is a very simple way for that object that you are actually representing with a single point, right? That is actually you are getting now P prime. Now, if we had a actually object at the beginning, say like you had an object like that, you have other 2 points, and now the same rotation function with that 90° rotation of that point, if you do, then actually definitely you will find the different orientation of that object. Okay, you will find P1 in here, then you will actually if you actually rotation actually happens, what it is also have a 90° for this one, this is also happen a 90° for this one. So somehow you will get actually different position of them, and if you just add them, then actually you will get the object in there as well. But it will be changed when it has a 90° rotation for this any object, 90° rotation, and that means actually it's coming almost in here, this point is coming almost in here. Okay, this one is actually maybe going in there, this is also coming in here maybe. So kind of an object orientation will be something like that. Okay, now we cannot actually see at this moment, as we are actually only making taking it more simple for one of the point, just for understanding that what actually happens for that rotation. Okay, do you understand? In your exam you will not have this problem, because this is so simple, only you just apply this and you can find it, right?
Yes, sir, definitely.
Okay, just for basic understanding, we are going through this actually, the problem for discussion. All right, now we will try to move our problem also in little bit in three-dimensional actually understanding, because so far we discussed about x and y value, we also now will discuss about z value, but it is actually in the homogeneous concern, means actually always same. So always same, then we can define that actually in only a value of 1. Okay, every two-dimensional point can be easily actually represent in this coordinate system. That's actually called the homogeneous coordinate. Now if we have a point, say x and y, and in 2D actually representation, we take that one in the new space, which is called x, y, and 1. You see in here, that's actually the homogeneous understanding. Why we are doing it? Because every point that actually have that x and y, somehow it has been actually defined already in a three-dimensional space. Like if we have 2 and 4, we can represent in many ways that 2 and 4 in three-dimensional space, like 2, 4, and 1. Okay, now if it is 2, 4, and 1, then 6, 2, 12, and 3. 3 in divided by 6 is 2. 3 divided by 4 is actually 12 is actually 4. So we can actually, you see that they are actually the same, that our understanding in the homogeneous coordinate. So homogeneous coordinate, we are always actually identifying that z coordinate is actually always 1. Then if it is actually the same 2 for 1 can be also 8, 16, 4. Look at the proportion. 4 into 2 is 8. 4 into 4 is actually 16. So that's actually also representing that 2 and 4. Okay. So 2D to 3D, very easily we can actually map back. Like when we have 15, 6, 3, that means actually it is 5 and 2, because 3 into 5 is 15, and 3 into 2 is actually 6. So 5 and 2 is actually in the two dimension that we can actually put that back, right? So then actually it can be said it's a homogeneous coordinate. So what it should be, 60, 40, 10 in two dimension, 6 and 4, right? So that's actually very easy, as you can see. So our main concern is that one that we are actually checking for three dimension. That means your depth, your distance from the actually in the space is always equal. Okay, that depth of that system is actually equal. So all the points along each line can be mapped back to the same point in the two dimension, gives the coordinate system, and it's called actually the homogeneous coordinate. Very easily that we can actually map back. So if we just consider in three-dimensional perspective, that say like if we have simply that mm, three-dimensional perspective, it has been actually said. So it's a three-dimensional object, as you know. So this distance in between that we are actually seeing this part or that, this distance is always actually 1. So we are actually having in such a cube our understanding in homogeneous coordinate, that whatever we can see for x and y coordinate in here, that is actually depth is always actually same. So that the three-dimensional point we can easily actually map back to the two-dimension, right? So this value is actually indicating this is 1. So for any value which is having say 5, 7, so we understand that 5, 7 is nothing but in three dimension is actually 5, 7, and 1, right? Do you understand actually that homogeneous coordinate why we are saying, or what actually are they?
Sir, in general, we consider 570, but if it is on, then it's homogeneous. Is it so?
Yes, that's when you say 0, that means actually there is no depth you are considering. Here we are actually considering a equal depth in everywhere.
Yes, sir.
Do you understand? With some value, because end of the day some point actually you can map back. When you have a 0, then actually you cannot do the map back. So if we have actually the divisible, that value for that z coordinate, Okay, so that if we have 5 in the z coordinate, that means this point is actually say like 20 and 10, indicating this is in the 3 dimension 2 dimension that actually I can represent like 2 and sorry 4 and 2, right? So 4 and 2, that point and this point is actually same. That's actually the advantage for having that coordinate, and we are taking that one for in 3 dimension. That's why actually we need it. Okay, can you see the slide?
Yes,
Yes,
sir.
sir.
Okay, all right. Now that actually the homogeneous coordinate. Now we take our that matrix. So for actually we have considering that in the column vector of the 2 dimension. Now we will go for actually 3 dimension. Just our this all this transformation function that actually we have discussed. Those are actually you can see in translation. At this case of the translation, the new point that x and y prime would be actually the translation factor that actually we have taken in that 3 dimensional matrix, and then actually the old point that we have in the dot product. Now what actually it is tx and ty, or dx or dy, if you can remember. So in the x coordinate is tx, y coordinate is actually ty, and the z coordinate is actually 1. Z coordinate is 1 for everyone. That is actually true, right? And this is actually 3 dimensional matrix that actually we have done, indicating the x coordinate value, y coordinate value, z coordinate value. If we do multiplication, then actually you get that translation value. The rotation the same way, that x prime y prime, the rotation function we had cos theta minus sine theta cos theta, and x y, that the old point that we had. Now this is actually the third one actually, that is that z coordinate value for the coordinate homogeneous coordinate, as the other actually this part value is actually 0. The same thing for the scaling as well, s of x and s of y. As you can see, remember that was the matrix in 2 dimension. Now in the z is actually only 1, and all are actually dot products. So we know that if we do that dot product of these two matrix, then actually we'll get the value for that this x and y, the x prime and y prime. That means the new points that actually we get. Now, this matrix that actually, whenever we are thinking about individual function, uh, literally actually in real life, the individual function does not happen. It happen in a combined approach, like rotation, then coming maybe translation, then coming maybe rotation. Like this way it happens. We say it like any event, like that day maybe in the example we have discussed, that you are watching the bus is coming towards you. Every moment the bus is coming very close to you, the translation factor is changing. Simultaneously, the scaling has been changing. The size of the bus is getting larger now, right? In your view, because this is part of the image. Naturally, what happened? Is it in real life the started to be getting bigger the size? It is not. It is again your actually perception, and I already mentioned very start of the beginning of this course that what actually you see is sometimes you can define that as an illusion. Okay, what actually your brain can perceive, that actually you see and feel. So whatever we can feel and see, that is actually part of our actually the image generation technique. So that the scaling that we are actually saying, that you are seeing that the bus is actually getting larger because it's coming close to you, and say like some it actually falling down on roadside, and that time the changes of the image of that object of that bus is actually getting some degree of orientation as it is actually changing. Now this is actually can be done um, in composite manner, or we can say in a combined manner. It can actually happen. So our main actually The study will be this composite of the transformation. We understand already now about translation, rotation, and that scaling. Now we will apply that in some of the composite format. Okay, and this composite format, to understand, that will be important for your exam. You will have the problem on base of it. You have to do that with the calculation, applying the formula, and also actually show that on the graph activity also we have. So also whenever you go for some of the animation, that time you will see that composite activity is actually important, because your object is not only moving from one place to another place simultaneously, maybe you are also applying that the changes uh, with some other rotation or maybe scaling and all other these functions. Okay, so that we are going to do. Already we have defined this transformation function according to the matrix basis. Okay, so we are going to actually work with matrix basis, as you can see. So matrix to matrix, that activity. Now one case, whenever we are doing this matrix dot product, we know that we can take it maybe this row and column wise, so that we can actually get the final value for this one. But when we will have multiple function together, then what should be the order of that operation? Okay, so that like translate, then rotate comes. So multiple number of that matrix that you have. So definitely this matrix, their activity has to be done in some order. Otherwise, the values should be different. According to that function, that actually multiplication, especially for the matrix, whether they are actually associative nature or not. Associative means actually what? AB first, then C. Is they equal? Maybe is it actually equal with A and BC? That means BC were actually doing first, and then actually doing with A. Is it equal to this one? If we do in the matrix, you will find they are actually equal. Okay, so we have taken actually the same component A, say like this one, A. This one is B, and this one is C. Now we are actually, for the associative nature, we are doing this first two, and we get actually doing like AB, EG, as you can see, AB and EG. So AE plus BG, and this one is CE plus DG, CE plus DG. This one is actually that AB, so AA plus BH, AF plus BH, and CF plus DH, CF plus DH. Now this one is actually with the C that actually we are doing, and finally we get this one. And now in the next case, that we are doing B and C first, so that B and C component, that whenever we have done, we get this one, and whenever actually we do that with A, then actually we get this one. Now the components, if you check the AEI, we have the BGI, we have the AFK, we have the BHK, that indicating this two of the multiplication is actually are equal, so that they are actually associative. So matrix multiplications are associative if you do it, but is it commutative? AB, and if you change the order, that BA, are they equal? In algebra it is equal, as you can find, but in the matrix you are not. When you have actually real number, you will find that how AB EG, if we do so, AEBG we get, and we get AF and BH. Now A and B, if it is there, like BA will be same if we have, so that B and A, if we do that, then actually say EA plus actually FC, and here actually we get B plus FG. You see the components are getting changed. Okay, so they are not actually commutative. So matrix multiplication are not commutative. So you need to understand that whatever the order we are going to have in this actually composite transformation, then the order is very important. You cannot change any order. If you change the order, your entire actually form calculation will be wrong. So that if we understand with the diagram is more easier. We are going to stop in here as the time is up. So look at the transformation function, we are considering as same, like from that perspective that ABBA is a commutative or not. So translation first, then rotation. The same value, if we apply the rotation first, then translation, they are not same, so they are not commutative. So translation, this object, I do translation for some value, say like that 5 unit, some value of the 5 unit, the translation factor dx and dy I have applied, and the object comes in here. Now I apply say 80-degree rotation, sorry, say like maybe 60-degree rotation. Now the object is actually moving in here. Okay, so first I did 5 unit of translation for x and y coordinate, and then done 60-degree rotation, then we found in here. Now the object from the same position, earlier also we had in the same position, that I apply 60-degree rotation, so the object is in here, then I applied the same unit of the translation, then the object goes in here. Now you see the position of the two objects, they are in a different in the space. So we can understand this order cannot be changed. Okay, so that cannot be changed, or we cannot consider that this order, if it changed, then we will get the same actually value. After applying the same value of this function, you will get yourself in a different position in the space. Okay, so that's why this order is important. So next class onwards, we are going to do actually composite transformation. 3 we had the composite transformation. Let's see that all 3 can we do or not. Okay, we'll do that actually according to using the formula for it, also actually the breaking down the formula. All right, so I hope that I'll see you in the class. Not in the class, I must say, that is an extra session in the evening. We will try to discuss about OpenGL with the relationship with this activity as well, with the translation, rotation, and a scaling factor as well. Okay. All right. Do you have Alif Laila Jannat?